Good afternoon, everyone. Good afternoon, everyone. Welcome to the industrial session. My name is Tintin Wang. I'm happy to serve as our session chair for this session. So today we have 5 presentations, and each presentation will include 15 minutes talks and 3 minutes Q&A. So let's welcome the first speaker. The title is Mining High-Frequency Risk Factor Collections End-to-End while Transformer.
Okay. Hello, everyone. My name is Chen Li from Computer Network Information Center, Chinese Academy of Sciences. Instead of my colleague, Wen Yan, I will do this talk, represent our group. Okay, today's topic is mining high-frequency risk factor collection end-to-end through transformer. And let's start camera. Okay. Is it work? 我打开了那个 camera，是这块吗？这个是这个吗？那我要重新说吗？哎，OK， 行，那我重新说呗。OK。Hello, everyone. My name is Chen Li from Computer Network Information Center, Chinese Academy of Sciences. Today, I will sorry, I will do a talk represent our group, and today's topic is mining high frequency risk factor collection end-to-end through transformer. And let's start with some background. We all know risk factor is an important issue in quantitative trading, even in the whole finance technology. In quantitative trading, transforming historic stock data into interpretive and formulaic risk factor helps identify market volatility and risk. Traditional risk factor include beta, size, and values, and momentum and liquidity. These factors have widely used, but they often fail to capture the dynamic nature of markets and non-linear relationships. Formulaic risk factor can be represented as binary trees, which nodes is constant of the unary operator and binary operators, and leaves is constant of the input factors. In our area, is often high price, open price, close price, and so on, and also has some constant. We all call it parameters, right? And besides of the manufactured factor, lots of work focus on mining risk factors based on the AI method. However, while neural networks have made a significant progress in extracing potential risk factors, their applications is mostly limited to the feature extraction. The challenge here is that this method often lacks a structured and explicit approach to design the risk factor, which can hinder their interpretability and applications in more complex scenarios. Now, let's explore a different perspective. Instead of treating the mathematical expression as more formulas, we view them as a language. This approach from the idea that symbolic method can be treated as a rich, structured language, where mathematical expressions serve as meaningful sentences. So our new frameworks is proposed. So it is called HRFT. During the training phase, we generate synthetic risk factor expressions use a tree-based approach with operators, variables, and constant. We create input samples from a mixture distribution to enhance diversity. Our output features include open, close, high, low, value, and so on features, all proposed using word expression. We also use prefix expressions to represent high frequency risk factor. For example, we have the function fx and can be encoded as expression as below. Our transformer models is trained from structures with 16 attention heads and embedding decision is 512 and totaling 86 million parameters. Moving on to the inference phrase. Here, we refine the predicted constant using the BFGS algorithm to improve accuracies. And we also apply a scaling process to handle varying input distributions. This ensures that our model can effectively generate risk factor for diverse datasets. In our experiments, we compared our method against several benchmark and in US market and Chinese market. We use varieties of metrics to assess performance, which are all indicators that can effectively assess risk. These results are quite performing. Our main results showing that our HRFT achieves a 13% higher investment return compared to other methods in SR bench. Additionally, our inference time is much faster than the compared method, making it highly efficient for the real-world application. We also conducted the backtesting experiments to validate the effective of our approach. The backtest is conducted over a 1-year period in China high-frequency transaction market. You can see the result in table 3. Our method can give a very simple formula and can achieve a higher cumulative net value than other comparison method. The mandate risk factor that demonstrates strong predictive power and confirming that our method can effectively capture the market volatilities. To sum up, we propose a data generator for end-to-end for high-frequency risk factor mining. Our method employs hybrids, symbolic and nomic vocabulary, and trains transformer models to generate the formula factor without relying on the predefined structure. By refining the constant use at BFGS, we effectively address nonlinear issues. Our approach achieves a super performance with a 30% higher in investment return and significantly faster inference time compared to the existing method. Thank you for your attention.
Okay, thank you for your presentation. So, any questions?
So where do you get your financial backtesting data?
Okay, we get our data from Venn database, which is a very comprehensive database, micro economy database.
And have you verified the main risk factors in the subsequent asset allocation stage?
Oh yes, our back test in investment test our risk factor based on the MV models and found it can give a much higher returns compared with other method.
Okay, thank you.
Thank you.
Any other questions? Okay, thank you
thank you.
again. Okay, so the first talk is HedgeAgents, a balanced, aware, multi-agent financial trading system. Welcome the speaker.哦，你想那个，看行不行？哦，有，这是刚刚现在的，现在就这个。
Good afternoon, everyone. I'm Xiangyu Li. Today I'm excited to share our work called HedgeAgents, a balanced, aware, multi-agent financial trading system. This project is jointly developed by South China University of Technology and BitDance, combining automatic insights with industry experience to explore robust and intelligent financial decision-making. Today's financial markets are getting more and more complex. Asset allocation is no longer straightforward, with global assets under management expected to reach $155.40 trillion by 2025. The types of assets keep growing fast, and investment across different countries are becoming more common. At the same time, we are witnessing an explosion in financial data, growing at a yearly rate of 42.6% between 2020 and 2025. Notably, unstructured data such as news articles and social media posts now makes up about 80% of our financial data. Moreover, asset connections are getting stronger. Since 1990, cross-asset collaboration has more than doubled, and during market shocks, assets tend to move in the same direction, making it harder to spread out risk. These factors underscore the need for more and more flexible ways to manage assets. In the rapidly evolving landscape of financial markets, advanced models like DeepTrader and FanGPT have showcased impressive capabilities under stable conditions. However, they don't work well during market crash. For instance, in periods of rapid market decline, a majority of these methods yield negative returns, with some experiencing losing exceeding 15 to 20%. This underperformance is largely attributed to the absence of integrated risk management strategies within these systems. Consequently, their practical utility in dynamic financial markets remains limited, highlighting the need for more robust and adaptable modeling approaches that can witness the market volatility. However, as we explore the current modeling methods, we encounter significant limitations in both traditional methods and LLMs. Traditional methods struggle with market ups and downs, rely heavily on manual iteration, and are often unable to process unstructured financial data effectively. Moreover, their black box nature makes the outcomes difficult to interpret and verify. On the other hand, LLMs introduce a new set of challenges. They are extremely expensive to train, suffer from slow inference speed, which is critical in the same sensitive trading, and tend to underperform on temporal prediction tasks. Furthermore, their hallucination problems poses serious risks when reliability is paramount. To address these limitations, we project a novel multi-agent hiding system named HedgeAgents. Our contributions can be summarized in 5 key points. First, this is the first work to incorporate hiding strengths into a multi-agent financial trading system, aiming for real-world robustness. Second, we designed a structured Hedges portfolio consisting of 3 domain experts and 1 fund manager, all coordinated by a LLM acting as the central cognitive engine. Third, we implement 3 types of internal conferences, enabling the agents to debate, reflect, and dynamically adapt their strategies. Fourth, in extensive experiments, our system achieves a total return of 400% over 3 years with an annualized return of 70%, even under extreme market volatility. Moreover, our method outperformed all baselines on the PRUDEXB benchmark, but this figure mistake, achieving leading results across 6 evolution dimensions. Finally, each agent is equipped with a memory system that retains human-like investment experience, supporting long-term learning and decision-making. To address the challenge of real-world trading, we designed a multi-agent framework inspired by how human hedge funds operate. In this framework, we introduced 4 agents, each taking on a specialized investment role: Bitcoin, Dongchuns, and Forex experts, led by a hedge fund manager. Each agent leverages expert-level algorithms, memory augmented retrieval to analyze real-time, multi-source, and multimodal financial data. To ensure effective teamwork, we built 3 team systems: target allocation, experience sharing, and extreme market conferences. So agents can exchange information, adapt strategies, and make collective investment decisions. This structured coordination allows the system to operate much like a real investment team, strong, informed, and responsive under uncertainty. We evaluate hedge agents against the 3 types of baselines: rule-based stress RL agents, and LLM-based measures. Firstly, RL agents like deep traders show clear advantage over rule-based models by better coupling market partners and adapting to uncertainty. Secondly, LLM-based measures such as FuXi-GPT, FuXi-agent perform better in risk-adjusted metrics like sharp ratio and camera ratio, thanks to their ability to understand multimodal information. Most importantly, our HedgeAgents outperforms all baselines across all metrics. It achieves the highest yearly return of 71.6%, the lowest drawdown, and the most diversified portfolio. This performance is driven by three key design choices. One, strategic budget allocation and careful risk management and robust multi-agent collaboration. Together, these features enable HedgeAgents to maintain strong returns while dealing with changing markets. This figure shows the total returns of our methods over the 3-year test period. As shown, HedgeAgents keeps going up steadily and consistently with all baselines. In particular, during the sharp market downturn in May 2022, most baseline methods experienced large drawdowns, but HedgeAgents remained stable and even gained value. This confirms that our approach not only achieves high returns, but also handles market trends well, showing real-world strength and reliability. In this part, we remove the HedgeAgent setup and evaluate how each model performs on individual assets. The goal is to test that their ability to different market types, Bitcoin, stock, and Forex. As shown in the curves, HedgeAgents consistently achieves strong results across all settings, confirming its robustness even without diversification. In this slide, we present an operation study to evaluate the effectiveness of the three teamwork mechanisms in our multi-agent framework. We found that each model plays a distinct and crucial role. The ESC improves defeat and reduce tail risks. Its removal leads to the largest drop in the ENT score. BAC is keen to maximizing returns with its absence causing the steepest decline in ARR. EMC strengthens risk control. Without it, the model suffers significantly higher drawdowns. Together, these models form a strong system that ensures balanced and robust performance across all metrics. To verify whether the system's performance is solely dependent on the power of LLMs, we conduct the evaluation study using LLMs of varying partner size. As shown in the radar plot, all 6 models perform well with similar steps, indicating the robustness and stability of the HedgeAgent framework. Even when using the most powerful model, GPT-4, the cost remains very low, just 17 cents per day over the 3-year back test. To better understand our frameworks, we visualize the decision-making process of both a single agent and a hiding expert. These visualizations highlight the thinking steps taken during decision-making. For a deeper dive into these mechanisms, feel free to visit our project homepage. Our agents not only react to data, but also learning investment partners similar to human traders. For example, they recognize seasonal effects like the close rally, follow large cape movements during rebounds, prefer low volatility assets for stable returns, and utilize the last 30 minutes of trading to detect short-term opportunities. These behaviors so that the system can acquire and apply critical investment strategies. The page presents the real-world investment performance of our system during a live backtesting period. The results speak to the system's fascination. A total return of 68.44% indicate exceptional alpha generation in diverse market conditions. Importantly, the systems achieve this with strong risk control, evidenced by a sharp ratio of 2.1 and a maximal drawdown held to just 10.92%. The winning rate of 58.19% further confirms the consistency and long-term potential of the strategy. Thank you for your time and attention. If you are interested in learning more about our work, feel free to visit our project page or get in touch. We are excited about where this research is heading and looking forward to further discussions. Thank you.
Any questions?
Thank you for your presentation. And I have two questions. So one, I saw your presentation mentioned that you include the experts in your framework. So I just wonder, like, it's a real person, or it's just the profile created by large language models, those experts?
Pardon, I don't know what you mean.
You know, in your framework, you include experts, like those, yeah, like 3 hedge experts. Probably last slides. Like structure team, the 3 hedge experts plus 1 fund manager. So this is created by like large language models, or they are real experts, or they're real person, or yeah.
Can you speak in Chinese? Oh, my English is terrible.
So maybe you can discuss that offline.
Oh, okay, thank you.
It's about like I saw your perfect performance about your return, your back testing. The question is that when you each time you run the back testing, does they so the results is like small variance, means each time you run your test it get better performance than the market, or it's random. So sometimes it works well, but sometimes it works bad. Is the result stable or not? Yeah, we can discuss that later. Yeah.
Sorry.
Any question?
First of all, thank you for your presentation. So I see you are using a supervisor model or architecture to orchestrate your agents. What are some of the guardrails that you are using to make sure that this thing doesn't hallucinate, as well as are you using some sort of a static workflow or it is dynamic?
Pardon. Oh.
So is your workflow, like the way the agents communicate with each other, is static or dynamic?
Dynamic.
Like the framework is stable, or those framework are communicate with each other, or like when they go through it, like dynamic? Yeah.
Oh, a dynamic, a non-subject. Is each agent equipped with 23 tools, and his decision making is not manual. It's not rule based, but it is evolution itself, and the decision making is all day, and every day is different.
Okay, so in that case, how are you preventing them from hallucinations, right? In terms of agentic hallucinations, what sort of guardrail mechanisms do you use that it doesn't do bad?
Too bad.
Okay, due to time limitation, so if you have more questions, you
Oh,
can
sorry.
discuss with the speaker offline. So sorry. Okay, so let's move to the third presentation. FuXi-alpha scaling recommendation model with feature interaction enhanced transformer.
Good afternoon, everyone. My name is Yufei Ye, from University of Science and Technology of China. Sorry. Today I'm going to introduce our work on FuXi-alpha scaling recommendation model with feature interaction enhanced transformer. Let's begin with the background of our research. Although traditional deep learning recommendation models based on discriminative approaches have dominated this field for many years. Sorry. Recent breakthroughs in autoregressive sequential recommendation models have opened up new possibilities for generative recommendation. Compared to deep learning recommendation models, autoregressive sequential recommendation models are more possible to demonstrate scalability. So we followed this route. Sequential recommendation aims to predict users' next item based on their historical interactions. An important part of this is the temporal information. Different orders of historical interact items or different time gaps between these interactions may represent different user intentions. Despite sequential recommendation, traditional deep learning recommendation models are also a crucial part of the recommendation systems. And a key concept in these models is feature interaction, which is used to guide us how to design these models. Typical feature interaction refers to how we model the relationships between these features. Typically, we categorize it into explicit and implicit interactions. Take DCNV2 as an example. The model has a cross network and a deep network. And in the cross network, we model we use a bilinear function to model the relationships between the features. We call it the explicit feature interaction. But in the deep network, it use a neural network to fit some function to model the relationships. But we don't know the exact form of this function. So it is called implicit feature interaction. In generative recommendation systems, we can think each item is a feature of the sequence, and the things like the interaction time can be seen as features of the item itself. When designing this models, we need to consider how to enable interaction between the features of the sequence and how to conduct interaction among the features of the items themselves. Previous work on modeling temporal and positional information still have some shortcomings. These methods often directly at the embedding of temporal and or positional information to the attention map or the query matrix. But we think this direct way isn't very helpful for the model to effectively distinguish these different types of information. And on the other hand, oh, sorry. Uh, and on the sorry, why 2 minutes? On the other hand, some work diminish. Oh, sorry. On the hand, some work reduces implicit interactions. They excessively rely on explicit feature interactions, such as the attention mechanism. But we think that in deep learning recommendations models, explicit and implicit feature interaction are always difficult to separate. They need to integrate both to achieve better performance. So we think relying solely on explicit feature interactions may limit the model's expressive power. To tackle these challenges, we introduced FuXi-alpha, which features an adaptive multi-channel self-attention layer and a multi-stage feed-forward network. The adaptive multi-channel self-attention layer separately handles temporal, positional, and semantic features. For the semantic channel, we still compute the query key attention as usual. But for the temporal and the positional channel, we directly use the biases generated by the relative attention bias model to as attention maps. The multi-stage feed-forward net involves a two-stage implicit feature interaction. In the first stage, it simply integrates the outputs from different channels from the previous layer and combines the residuals. But in the second stage, we use the feed-forward network to enhance the implicit feature interaction. Here's a simple comparison between the attention layer with relative attention bias and our adaptive multi-channel self-attention layer. As demonstrated here, such a decoupled modeling approach enable temporal information to achieve enhanced representation capacity rather than being confused with semantic information. And here we have the visualization of different attention maps for the 3 channels in the FuXi-alpha. You can see that each channel's attention map has this distinct pattern. Mixing them together might indeed make it harder for the model to effectively learn these different features. For the experimental part, our offline experiments were conducted on 3 public data sets and 1 industrial data set. The industrial data set is constructed from the Huawei Music app. As this table presents, FuXi-alpha exhibits consistent superiority over existing baseline models across all 4 datasets. Here are other experimental results. The table in the upper left corner presents the online A/B test results of FuXi-alpha. It shows our model demonstrates significant improvements across both online evaluation metrics. Moving to the lower left corner, it presents the results of the efficiency comparison. Although our approach increased the computational overhead, but it still maintains similar efficiency compared to HSTU. In the upper right corner, it presents the ablation studies of FuXi-alpha. The results confirm the effectiveness of each component in FuXi-alpha. Finally, the lower right corner illustrates scaling experiments conducted on the industrial dataset, providing preliminary evidence that our model exhibits scanning law properties. In conclusion, FuXi-alpha offers a significant advancement in recommendation models by effectively enhancing feature interaction. We believe it has a great potential for the large-scale recommendation systems. That's the end of my presentation. Thank you for your attention.
Thank you. Any questions?
Hi, thank you for your presentation. So you deployed it to the music service, this like transformer, and this is the only model like from start to end that generates recommendations, or you have some meta models under or after this model in the production?
So sorry, could you please repeat your question again?
Okay, I'll just ask another one. So is there any other limitations of this architecture that you want to explore? Like in some papers, people said that transformer architecture cannot count, like because it's music, you have many repetition when you listen the same song again and again, and some transformer architecture cannot count how many times did you listen that, and some other limitation like this.
You mean about the future directions of this work?
Do you think there is some other
are there-
limitation of this architecture that you want to address? Like some transformers cannot count how many times did you listen this item? Maybe 5 times, maybe 10 times.
Maybe about the efficiency. It has a quadratic complexity of the sequence.
Okay, thank you.
Hello, thanks for presentation. How big is the model that you actually serve? So what's the parameter count, or how many GPUs do you need to actually serve it?
Now we in our online experiments, the model size isn't very large. We use a single NPU to serve it. But I'm not very familiar with the industrial setting, because the online experiments were conducted by my mentor, Wei Guo. You may contact with him through email later. Thank you for your question.
Okay, thank you. Thank you for the presentation. I think one of my the major concern from my side is that the basic differences between your FuXi-alpha and the HSTU is that you re-added the FIFO network, right? So the purpose of removing FIFO network in HSTU is that the meta staffs want to reduce the complexity and just to leave the calculation to the multi-head attention, maybe just attention. So in your case, you added it back. May I know if you put like same level of parameters between FuXi-alpha and HSTU, the layers of like FIFO network and attention layer will be different. However, if you said give them a same amount of parameters, will the performance be better for FuXi-alpha compared to HSTU?
Could you repeat your question?
Okay, I'm a little bit okay. Let me rephrase it. So that the FIFO network in your architecture actually contains a lot of parameters, right?
Yes.
So in this case, if you remove this part of parameters into adding more layers of the attention layers, how will it compare to the your new FuXi-alpha and the HSTU?
You mean the scaling property?
Yes, yes.
We didn't compare this right now. My mentor only conduct the scaling experiments on FuXi-alpha in the industry data set. We maybe will have a look at this in the later.
Okay, thank you.
Yes, thank you.
Hello. My question is about the scalability of the system compared to HS2. So I think the assumption of HS2 is that once you reach a certain scalability, you can just rely on the implicit features of the user interaction to get high quality recommendation. So from your experiment, have you observed like the performance gap between your approach and LSTU, like how that changes with the scale of the data?
You mean the differences between our model and HS2 when the model size becomes large
And the data becomes large.
the data. We didn't conduct experiments about the data. 然后
Okay, that's okay. Let's take it offline.
Thank you.
Okay, so it's a time out. So if you have more questions, please feel free to discuss with the speaker offline. So thank you, everyone. Okay, the next presentation, generative retrieval and alignment model, a new paradigm for e-commerce retrieval. So the speaker doesn't appear in the session. Okay, so maybe we can begin the next one first. So, you final speaker? Yeah, you can. Yeah, first. Yeah, this presentation is about creator-side recommender system, challenges, designs, and applications.
Okay, now let's begin. Okay. Hello, everyone. I'm very glad to do my presentation here, and I am an engineer in Kuaishou Technology, and this work, the creator-side recommender systems, was done at Kuaishou Technology. Okay, here's the table of content. First, the motivation, and then the methodology, the experimental results, and the conclusion. Okay, now let's begin with the motivation now. We know that users and creators are two crucial components of recommender systems. The users consume items that they are interested in, and their feedback on these items will encourage the creators to produce more items in the future, and then lead to more satisfaction of the users in the future. Therefore, a recommender system needs to improve both the user experience and the creator experience. Okay, now let's consider a typical recommender system. In this system, the users send requests to the recommender system, and the system uses the matching or retrieval and ranking strategies to provide the most proper items which the users are interested in. Therefore, this kind of recommender systems, we should regard it as a user-side recommender system, which aims to improve the user's experience. However, what about the creator's experience in this kind of recommender system? Unfortunately, in the user-side recommender system, it is common that only a few items receive many exposures, while many items receive very few. In such cases, the creator's satisfaction will be harmed when receiving less feedback. We can also find that the creator's activity highly depends on the feedback they receive for each item. So we aim to find ways to improve creators' experience in the recommender system. Okay, existing approaches aim to create more opportunities for underexposed items. For example, we can use a score booster on items with fewer exposures. However, these approaches still focus on improving user satisfaction when distributing these underexposed items. However, users and creators respond very differently to different types of feedback. Let's discuss a short video platform. The user's watch time on a video is crucial for reflecting user satisfaction. However, the watch time is not visible to the video's creator, and therefore the watch time of a video cannot impact the creator's satisfaction. Therefore, our motivation is to build a new recommender system focusing mainly on the creator experience. Under this background, we propose a creator-side recommender system called DualRec because it solves the dual problem of the user-side recommender system. Now let's compare the user-side and the creator-side recommender system. The user-side recommender system receives users' requests and then finds the most suitable items for each user, while the creator-side recommender system receives items requests and then find the most suitable users for each item to improve the creator experience. Of course, these two kinds of recommender systems are very similar. Okay, this is our motivation on the creator-side recommender system, and then we provide concrete methods. Here we need to answer two questions. The first is what components are needed in the creator-side recommender system compared to the user-side recommender system? And the second question is we call the user availability issue. It's the difference between the user-side and creator-side recommender system. Specifically, in the user-side recommender system, candidate items are always available by the user. But in the item-side recommender system, we need to find users that will watch the items. But these users are not always available. We need to wait for the users to come to the platform. But the users may firstly the user may simply not visit the platform, and secondly, there may be many items allocated to one user, but a single user cannot consume too many items. So now let's deal with these two problems. Our key idea is that the users and the creators are two symmetrical components of the recommender system, and therefore, by interchanging users and items in the user-side recommendation items, we can derive the corresponding creator-side versions. Now, we provide some examples, including the retrieval and ranking algorithms. The first is the retrievals in the DualRec system. Typical retrievals include similarity-based retrievals and model-based retrievals. The similarity-based retrievals retrieve the candidates by the similarity services. In the user-side recommendation, there are two kinds of retrievals. That is the user to item retrieval. We call it U to U to I, and it's based on the user similarity service to find the similar users and then to retrieve the similar users' historical interacted items. And the second is the U to I retrieval based on the item similarity service. It retrieves the items based on the user's historical interacted items and finds the similar items to retrieve to the users. And in the item side recommendation, the corresponding retrieval methods can be mirrored to the I to U retrieval based on the item similarity service and the I to U retrieval based on the user similarity service, and it's all mirrored. So therefore, the user side algorithms can be easily mirrored to the item side versions without extra training of the similarity service. And a similar phenomenon can be found in the model-based retrieval, and the most typical model-based retrieval is the two-tower retrieval, which utilizes an approximate nearest neighbor index, that is the ANN index, to find the most relevant candidates. The users and the items are symmetric in the two-tower model. Therefore, we do not need to train a separate two-tower model, and we can use the same model as the user side algorithms. And the only thing we need to do is to retrieve the target users most similar to the given item. Therefore, we need to build a user ANN index rather than an item index in the user side recommendation. Okay, that's the retrieval. And the ranking algorithm is also very similar. The ranking module contains two components. That is the prediction and the score integration. The prediction model predicts the user feedback on items. Here, we need to adopt some effective skills to provide more accurate predictions on long tail items, because most of the items are long tail items, and we need to produce accurate prediction to them. And here there are many methods, and we just adopt two major methods. The first one is to augment the training sample by dropping the item ID feature and then train the original sample and the augmented sample simultaneously. And the second is to add more item side features. And in the score integration model, we need to merge the multiple prediction scores into one single score. The score integration is somehow similar to the user-side score integration, but it focuses more on explicit interactions such as likes, shares, and maybe follows in the platform. And for example, the watch time, the weight of the watch time is very small in this score integration, or even if it is very large in the user side score integration. And moreover, we add a new user bias term to show different values of different exposures. Therefore, we show that typical retrieval and ranking algorithm can be applied to the creator side with just a few modifications, and this greatly simplifies the construction of the creator side recommender system. And the next problem is the user availability issue. We need to make sure that the users returned by the Durex system will visit the platform and consume the given item. In other words, we need to wait for the users to come. To achieve this, we add a user availability calculation module to maintain available users. Then, what's the available users? There are two properties. The first is that the user will visit the platform in the near future, and this property is obtained by a user activity prediction module. And then the second part is that the user has not been matched too many items, and this property is maintained by a user index service like the item index service. With the user availability calculation model, we can ensure most of the users returned by this system is valid. Okay, that's the total methodology, and then we discuss the experiments. We implement the Durex system in our Kawaii app, a short video platform with about 100 million users and 10 million creators. We should know that the A/B testing settings are also important in measuring the performance of creator-side metrics. And to measure this, we use a user-creator co-diverted experimental setting, and the users in the control group receive items only from the controlled creators, and the user from the experimental group received items only from the experimental creators. And this A/B testing enables us to measure the treatment effect from the creator's perspective. And the baseline is a user-side recommender system with extra boosters on new items, and like Berac. And we implement the Durex system step by step until the final version discussed in our paper. We use the number of items reaching 1,000 and 10,000 and the number of active creators as the matrix. And the experimental results show the effectiveness of the proposed Durex system over the baseline method. Okay, the last part is some discussions. First, we find that the creator-side retrievals cover more new items than the user-side retrievals. With the same two-tower model, the user-side retrieval can only cover 13% new items, and the creator-side retrieval covers 41%, and the creator-side retrieval with the user availability calculation module covers 82%. Actually, the creator-side two-tower model differs from the user side only because it uses a user AN index rather than an item in AN index, and this simple change brings a significantly larger coverage. And the second is that the user availability calculation module ensures the performance of Durex by ensuring that the majority of the users are matched with an acceptable number of items. Okay, the last part is the conclusion. And we introduce a novel creator-side recommender system called Durex to find the most proper users for each item to improve creator experience. And the algorithm in the user side can be easily translated into the creator side with only a few changes. And the user availability issue in Durex can be addressed by a user availability calculation module. And we implement it in the online system, significantly improving creators' satisfaction. Okay, thanks for your time. And we are the overseas recommendation group in Kuaishou Technology, and we work on recommendation algorithm applied to the short video platform, including the retrieval, pre-ranking, ranking, and re-ranking algorithm, the entire recommender system. And we also work on code style algorithm and social recommendation algorithms. And this is our contact info. Okay, thanks for your time and any questions.
Okay, thank you for your presentation. Any questions?
Yeah, a cool presentation. So this is now in production, yeah, as I understand. And how frequently you recalculate this recommendation of users to items for some specific items, and how do you merge this when you recommend something to user? So I don't know, so 70% per user recommendation, 30% this item user recommendation, or how?
Okay. The first question is that how frequently we update the user's match to the items. We use a round robin manner to traverse all the items in our platform, and in our platform it is about 4 hours to traverse all the items. About the number of items the number of new items every day is about several millions. Okay. This is the first question, but second question, can you repeat it?
Can I just answer a bit more about the first question? Do you have some stop criterion for the item to leave this like base for?
Yeah. We the items received enough exposures will exit, and in our platform is about 10,000 exposures, and 2 old items will also exit from this system.
And the second question was about how do you merge this for when you recommend to user? I believe you have some quotas or like.
Yeah. Okay. We use the item size recommendation to obtain the users for the item, and then we use a result cage that is an inverted index to maintain this information, and the result cage the key of the result cage will be the user, and the value will be all the items the match to the user, and then when this user come, we will use a user-side retrieval to retrieve from this result cage, and there will be a score integration in the ranking of the user-side recommendation. This is the total process, and the quota of this creator side, I think it's several percent of the total exposures.
Okay, thank you. That's cool.
Okay, thank you.
Thank you for your presentation. Actually, my question was partially already covered, but I will maybe add one more specific question. So if I understood correctly, the main purpose of this system is to make sure that the new items, in your case, these are the videos, short videos, each of them receive some minimal number of views, and you use your system in a batch manner. So I don't know what's the frequency, but when the new videos arrive, then you calculate this the users to which you will show the video, and sometime after that, the video is shown to these users. Is that a correct understanding and correct understanding of the use case?
I think you are correct. You are correct, and we will promise a minimal exposure for each item use this system, but the minimal exposure is about only about several hundred, and the purpose of this paper is that this initial exposure will make the system learn these items well, and then the system can distribute these items more automatically. And so our metric is the exposures reaching 1,000 and 10,000. This is far larger than the exposure promising. Okay.
And one more question. Do you advertise this solution to your creators? Are they happy from this solution, that they know that maybe like more of their items will be shown to users?
We find the creator activity be higher, and this system has a performance gain on the creator activity about 3%, but it's very hard to verify that the new items produced by these creators are how valuable it is to the system. It is very hard to evaluate.
Thank you.
Okay, thank you.
Any other questions?
Oh, hi. So thanks for the great talk. My question is related to how this system is implemented in practice, because especially based on this study, it seems that the goal is to pretty much ensure the items gets a certain number of exposures. And for instance, after it reaches 10K impressions, you remove them from the candidate pool. So I think one potential downside is that based on this, it might exacerbate the effect of the rich gets richer effect, which is commonly seen in recommendation systems for the low exposure candidates. Have you tried to measure this effect, for instance, by looking at the Gini index of the impressions for this candidate item beyond the number of items who have reached 1K or 10K impressions? Thank you.
We do not measure the Gini index, but I think this will be the Gini index will be improved, but I did not measure it because the number of items reach a small number of exposures will be larger than the baseline method, and I think the exposures will be more on the underexposed items.
Thank you.
Okay, thank you.
Thanks for the great talk. So I think intuitively, if we increase the based on the creator oriented recommender system, the users may not get the most relevant items or most relevant short videos. But in the paper, it seems that you indicate there is not a significant degree in user satisfaction. So what will be the rationale behind this phenomenon?
I think it's a good question, and I think the users relevance will definitely be decreased, but sometimes this trade-off will be very small, and when we work on an online system, we will find the decrease is not very significant. So, but if you increase the quota of the creator side recommended system, for example, if we use 10% quota to do this, that would be definitely decreased. Yeah.
Okay, so you're saying there is a trade-off, but you just want to find a sweet spot where you don't degrade the user satisfaction that much, but increase the creator's satisfaction a lot.
Yeah.
Sounds good.
Okay. So if that's all, if the final speaker doesn't attend, so maybe that's all content about this session. So thanks everyone. Thanks for attending this session. Thank you.
Thank you.